Good morning, ladies and gentlemen. This is Ben Keyser with Applied Flow Technology. I want to thank you all for listening in to today's webinar, where I'll be talking about the Goal Seek and Control module, which is available for AFT Fathom and AFT Arrow. This webinar is being recorded, and so if you are listening in live, then you'll be able to watch the recorded version at your own leisure later on. You can also forward the recording around to your colleagues, and then you will be sent the link to this recording sometime later this week. If you are listening to the recorded version, thank you for listening in, and I'm going to go ahead and get started. My name is Ben Keyser with Applied Flow Technology, and I'm going to be demonstrating an add-on module for AFT Fathom, which is an incredibly useful and powerful tool. So we have several add-on modules that are available for all of our different products. If you go to our website, aft.com, and the AFT software overview, this is where you can get a good overview of all of the different AFT software products that we offer. If you then click on any of those, it'll take you to that specific product's web page, and you can read about the details on what that software is doing. But if you scroll down to the bottom, this is where you can find the section on our add-on modules. So these are really useful tools that you can purchase in addition to AFT Fathom that will dramatically enhance your flow modeling capabilities. And today I'm going to focus on the Goal Seek and Control module. So the Goal Seek and Control module, what it will do is it will automatically change your input parameters in order to help give you your desired results. So it saves you from the hassle of having to do manual iteration on various parameters. It's a lot like Microsoft Excel's Goal Seek tool or Solver tool, but it's way more powerful here. And I'm going to demonstrate a few examples that will go into detail about how you can use GSC. So this is where you can find the basic information of the Goal Seek and Control module. If you're interested in giving it a try, don't hesitate to reach out to us and give us a call or send us an email, and we'd be happy to set you up with an evaluation for the GSC module. So I'm going to go ahead and move the website out of the way, and I'm just going to jump right into the software and get started here. This is a very simple example of a piping system which has gravity flow. And when I say gravity flow, it means the flow rate that is driven through the system is based upon elevation differences. So all of these pipes here are liquid full. When I say gravity flow in the context of AFT software, I'm not saying open channel flow. That's not something that we model. It's an important distinction that I want to make there. So we have two supply tanks. One of them is at a 40-foot elevation, another is a 35-foot elevation, and then we have a discharge tank at a 10-foot elevation. And so the two supply tank flow rates meet together, and then there's a flow control valve here in the system, which will control the flow leading into the discharge tank. So here's a situation where the Goal Seek and Control module would be really useful. I know from a flow measurement that the flow rate in this particular pipe coming out of supply tank B right here is flowing at 800 gallons per minute. Okay, so at 800 gallons per minute, that's my flow. I don't know what the flow rate is here in pipe P1. So what I can do in order to get my Fathom model to match results is I can specify a control valve here with a fixed flow rate. So if I was to go into this control valve right here and open it up, I could specify a fixed flow rate, and what Fathom will do is it will change the pressure loss across this control valve in order to meet my user-defined set point. Now the thing is, I don't know what my total flow rate is. So this value that I've specified right here, this is just a guess. It's nothing real at all. That's a starting point. So if I was doing manual iteration, what I would do is I would start off with a guessed flow rate there, and then I would run the model. And after I run the model, I would take a look at the results, which I could easily do here on the visual report. And on the visual report, this is where you can display your results right on top, right on top of the model itself. So as you can see here, if we specify 3,000 gallons per minute for the flow control valve, we're only getting 587 gallons per minute in pipe P2, and we need 800. So we need to manually iterate on that control valve's set point in order to give us the flow that we want in P2. Now, if you are really good at guessing and you have a really simple system that doesn't have a lot of complicated and complex interactions, it can be relatively easy to guess and check. What you can simply do is you can move your visual report to the side here and then simply go into the workspace, and that way you're displaying both systems at the same time. I'll hide my quick access panel. That would get a little bit more real estate. There we go. That makes it a little bit easier. There we go. So what I can do is bump this up, and we'll try 3,200. So we go up to 3,200, and we rerun our model, get new results, and then if we jump straight to the visual report here, then there we go. So I actually am closing in on an answer pretty quick. So I wouldn't need to change that value very much more. Again, if you have a very simple system and you're good at guessing, then it might take you, 5 or 10 runs to be able to dial it in on an answer. However, the goal seeking control module will automate that process for you. So here's a few different ways that you can turn on the goal seeking control module. I'm going to reset the panes here. All right. So one way to access the goal seeking control module is if you were to go to the tools menu, you can click on that tools menu there and then go down to activate modules, and this is where you can find all of the add-on modules that we have available. And this is the goal seeking control module. Now the nice thing is when you install the base AFT Fathom software or AFT Arrow software, all of the add-on modules are installed with it. There's no separate installation required for the add-on modules. That being said, you have to have a license for the add-on modules to be able to use them. So when I go to activate the modules, I would simply go in here and check the box. It'll look for a license, and if it finds a license, then it'll give me access to be able to use that module. And it didn't complain to me that it couldn't find a license, so I have access now. The other way is this button that is just to the left of the status light in the bottom right-hand corner of the interface. That's the other area where you can turn on the add-on module. So if I click on that right there, this is another way that you can access the modules. Again, same idea. You just check the box to turn them on, click OK, and then you've got access to the module there. All right, so my first step is done. I have activated the goal seeking control module. Now, let me open up my status light here and show you the checklist. So the default checklist here, typically, I didn't mean to draw that drawing. My mouse got caught on something. So by default, AFT Fathom has these 4 checklist items that are always displayed. Specify solution control, specify system properties, define all pipes and junctions, and then specify cost settings. And this option is usually grayed out and disabled unless you turn it on. So when you go to turn on the goal seeking control module, there is now a 5th checklist item that must be completed. Now the thing is, when you just turn it on for the very first time, it's not actually using it yet. That's why this checklist item here is grayed out and is disabled. So now if I go to the analysis menu, under goal seek and control, you have two options. One is you can choose to ignore the module. That's where you can just do a regular Fathom run. And if you've already specified all your goals and variables, you don't want to lose that information. So rather than turning on the goal seek and control module and deleting all of those goals and variables that you've already specified, simply click on ignore, and then you can just do a simplified run like you would usually with Fathom. Now, if I click on use, so that I can use the goal seek and control module, we now see that this option here is enabled. Now, it is initially checked off because we have not specified any variables or any goals yet. So if I was to open up that goal seek and control manager, I'm going to delete this actually. Okay. So this is the state that the model would be in if you've not specified any goals or variables. Where you can also specify goals and variables is analysis and then goal seek and control manager. So I can run my model and get results because, let me try this again. You'd be able to do a typical Fathom run because there are no goals and variables that are specified. And so I'm using an internal release of Fathom that's not available to the public for doing some testing of a new product that we have coming out soon. And so something must be conflicting with that. So what's supposed to happen is this is supposed to allow me to run my model. Now what I would need to do is specify goals and variables. So I'm going to go in here to the analysis menu, and then for goal seek and control manager, this is where you define your goals and variables. So the first thing I want to specify is the parameter that I want to change in my system. That's going to be the variable. So if I click on new variable, it brings in a new variable that I can change. There are different types of variables. You can do pipe variables or junction variables. For pipe variables, these are the allowable variables that you can change. Design factors, friction factors, the inner diameter reduction, which is the scaling option. You can also change the amount of insulation thickness inside of the pipes. All of those are very useful for helping you calibrate your model. So if you're trying to match your model to measure results, typically you're going to change those types of parameters to account for any scaling or buildup inside of the piping that will reduce the inner diameter or increase the frictional losses. And that's what you'll use usually to calibrate your system. And I'll show you an example of that here later today. So those are the pipe variables that are available. For junction variables, the first thing you do is specify which type of junction that you're going to create a variable for. And in my model, I'm going to do a variable for the control valve. So I'd click on control valve, and then you would have to specify which specific junction or pipe you would define the variable for. And then once you've done that, you specify the parameters. So in this particular case, I want to modify the control valve set point in order to achieve my desired results. So control set point is going to be the variable for my control valve. The next thing I'm going to do is I'm going to go to the goals tab. I'm going to specify a new goal. My goal could be a number of different things. There's different types of goals. There's a point goal, there's a differential goal, and it's hidden right now. It's not being displayed, but there's also a group goal. A group goal is if you select specific pipes and junctions on the workspace and use them to create a goal, then there would be a group goal. So that would be a group max min. I'll show you what that looks like in a little bit as well. In my model here, this is just going to be a very simple point goal. So I want the value, which is any of these parameters right here, to be a specific value at a point in my system. So in this particular case, I'm going to do a pipe goal. There are other goals you can do. You can do reservoir goals, you can do control valve goals, etc. My goal here is the volumetric flow rate. So I want the volumetric flow rate to equal 800 gallons per minute in a specific pipe. You can change your units here with the drop-down menu, and then the pipe ID is going to be pipe P2. So P2 needs to be 800 gallons per minute, and I'm going to establish that by changing the control valve set point accordingly. Now, when you're defining your goals and variables, you typically want to have one goal per variable. The reason for that is so that you have a more unique solution. If you have multiple variables to a single goal, then there could be a number of possibilities that would help you achieve that particular goal. And so there'd be not as unique of a solution in that case. So that's where multiple or having one goal per variable is important to keep in mind. All right, so once I click OK, I now have goals and variables specified. And what you'll see is a little red G and a little red V in front of the label, which stands for goal and variable. That's just a nice visual indicator on the workspace that tells you you have a goal and a variable specified for those particular objects. So now that that's all set up and ready to run, I'm going to go ahead and click on the green arrow that points to the right, and I'm going to run the model. And it converges very, very quickly. So what this is telling me is within 3 seconds, Fathom actually had to use the GSC solver just under 70 times in order to get an answer. So what it does is it runs the model to get a steady state solution based upon what your initial value is. So if you remember, I specified about 3,000 gallons per minute for the control valve. So what it does is it starts with that value that I specified, and it calculates the results to see if my goals have been able to be achieved. If not, then it will change this value little bit by little bit in order to get closer and closer to achieving that goal. So GSC actually had to do this 69 times within 3 seconds. Now, again, if you're really good at guessing, you have a really simple system, maybe you'd be pretty quick. But even if you went in and you were able to do this within 3 separate iterations or runs, GSC is still way faster than what you'd be able to do by hand. So let's take a look at the results. If I click on the output here, there's a whole bunch of results that I can look at. And as you can see here, I have 2,400 gallons per minute in pipe 1. I have 800 gallons per minute in pipe 2, which is what I needed. And then 3,263 gallons per minute in the remaining discharge pipes. Now, when you do the goal seek and control module, there are 2 new tabs that will appear in the general section of the output window, GSC variables and GSC goals. So if I go to the GSC variables tab, this tells me the answer that I need. This tells me that my control valve set point has to be 3,263 gallons per minute. So if I specify that set point, then I can go to the goals tab and I can see how my goals have been achieved. I desired to specify 800 gallons per minute, and I actually achieved 800 gallons per minute. So GSC did a very effective job of being able to figure out what my control valve set point is. The reason why I wanted to demonstrate this is because the goal seek and control module can dramatically further enhance your remote sensing capabilities with control valves. So if I open up this control valve here, there's different control valve types that you can work with. There's a pressure reducing valve that controls the immediate downstream pressure. Pressure sustaining valve controls the immediate upstream pressure. and then flow control controls the flow, obviously. So the reason why the control valve is very useful is because it'll automatically figure out the pressure loss to meet your set point. But the control valve is determining conditions immediately at the control valve, not anywhere else in your system. So what you might have is feedback somewhere else in your system where you might be getting information in any of these particular pipes, and that's what you can use to do remote sensing. So if you use the goal seeking control module, you can change your set point for any of these parameters automatically in order to meet your goals and variables for pressure or flow or temperature or velocity in other areas of your system. All right. So this is a really basic example. If I wanted to go one step further and take the answers that I got for the value of the control valve set point and turn it into a parameter, what I can do is after I do my run, click on the thumbtack right here. That thumbtack will transfer results to initial guesses. So if I click on that and then click OK, I go back into my control valve here. I then have the exact value that I needed for the control valve set point. So now I can actually go in here and ignore GSC, and now my control valve will do exactly what I want. So if I specify the exact input parameter, then look at that. I've got 800 gallons per minute in pipe 2. That's exactly what I needed. All right, so that's a very simple example of what the goal seeking control module will do. Let me bring one up that illustrates what a group goal would be. So give me one moment here. Okay, let's see. This is the one I'm looking for. All right, so this is one of our standard example help files, and this is a spray water system. So here I have a whole series of spray discharge nozzles, and this could potentially be for a fire system, or maybe it's a irrigation system. Basically, all you're needing to do is just distribute flow of a particular fluid to various areas through this spray nozzle network. And in the spray nozzle network, for each of these spray discharge nozzles, I'm using the spray nozzle option where I've specified a discharge coefficient, which is 0.6, and my discharge flow area is, that's the size of the hole that you are spraying through. So this particular example has a requirement such that each of these spray nozzles need to be able to deliver a minimum flow rate of 100 gallons per minute. In order for them to all flow at least a minimum of 100 gallons per minute, is you would change the supply pressure. So if I'm doing this manually, what I would do is I would start off with the pressure, which that actually is the answer. So let's say I start off with 80 psi-G. What I would do is I would run my model based upon 80 psi-G. I can go to the output window, and the easiest way to see this is to look at the spray discharge results. Now, as you can see here, there's something that I want to point out where the volumetric flow rate and mass flow rate through the junction column says not applicable for each of these spray nozzles. Why is that? Well, the reason why is because if I go back to the workspace here, I have one pipe coming in, and then I have spray coming out of the nozzle, and then additional flow going to the next pipe. So if we are trying to figure out what the flow rate through the junction is, what do you mean by the word through? Do you mean through the spray, through to the next pipe, or through some combination of them? The answer is there is no answer. It's ambiguous. So that's why for these spray nozzles that are in line with all of these pipes here, you will see not applicable for their flow rates. Now you will see a flow rate for the ones on the very ends. The reason for that is because there's only one through. It comes in and then it goes right out of the spray. There's no downstream pipe here. And so that's why those two spray nozzles have results. So if I switch back to my results there really quick, we'll see not applicable for all of them except for the two that are on the ends. So there's another parameter that you'll need to specify here. If you go into the output control window, let me circle it. The output control window can be accessed there, or from the tools menu. And so if you access the output control window and then go to the junctions button, there's another parameter called volumetric flow rate net at junction. That's the one that you need to use, the one that has the keyword net in it. That is the flow rate that is coming out of the spray nozzle itself. So if you add that parameter, which we've done right here, then you'll be able to see what the spray flow rate is coming out of the spray nozzle for each of those junctions. So as we can see here, not one of my spray nozzles is achieving the minimum of 100 gallons per minute. So I would have to continually bump up my supply pressure over and over and over again until I get a minimum flow rate. Now there's a really easy way to do this with the goal seeking control module. Now, obviously, you're not going to be able to have equivalent flow through each of those spray nozzles, assuming that your connected piping is exactly the same and your characteristics for each of the spray nozzles, i.e. the diameter of the holes and the discharge coefficients are the same. So if those are the same, then you're not going to have equivalent flow. So this spray nozzle here will get the most flow. This spray nozzle will get the least amount of flow. So what you would do here is you would use the group goal instead of a point goal. So, I mean, I suppose you could do a point goal. You could say, change the supply pressure here in order to establish a minimum flow rate of 100 gallons per minute at the ends. Because based upon the way that this system looks, it appears that those are the two hydraulically most remote spray nozzles. But that is not always clear, and I'll show you another example where it's not clear which spray nozzle is the furthest away. So you can't always just say, make my minimum flow rates be based upon these two specific junctions only. So what I'm going to do here is I'm going to go in and select all of these spray nozzles. And after I select my spray nozzles, I do have pipes and a branch junction selected as well. That doesn't matter. It's fine. I'm going to go to the Edit menu, and then I'm going to go to Groups, and I'm going to click on Create. And I'm going to give my group goal or my group a name, Ben's spray nozzles. And so as we can see here, when I created my group for Ben's spray nozzles, these pipes and these junctions were included in the group. Now the thing is, I don't care about the pipes in this group, so I could go ahead and turn those off. And I don't care about the branch, so I'm going to uncheck that. So once I create my group, my goal seeking control manager becomes a little bit different. So I've already got GSC turned on. It is currently being ignored, but if you go straight to the goal seeking control manager and you define your goals and variables, once you click OK, you have the option of enabling GSC right then and there. So here, my variable, which I've already added to the list of variables, is going to be my assigned pressure junction. That's what I'm going to change. So I went in here, my object type is a junction. My junction is going to be the assigned pressure, and I'm changing the pressure. You could also change elevation or temperature as well. Those are additional parameters you can modify. Then for my goals, let me delete all these to get the complication out of the way. So I'm going to do a new goal, and instead of doing a point goal, after you create the groups on the workspace, you'll see the group option appear. So I'm going to choose the group option, and there's two ways that you can do a group goal, either a max min or a total value itself. So the max min is what I'm going to use here. I want to make sure that my flow rate, my volumetric flow rate, is going to be greater than or equal to 100 gallons per minute for my spray nozzles. This is where you define your group. Since your object is a group in this case, you would specify your group accordingly. So as long as that is going to be putting 100 gallons per minute minimum, that's appropriate for my GSC goal there. All right, so I click OK. Let's see, I wonder if I missed something. Let me go back in really quick. Needed to apply that. One thing to make sure is that you actually check the box to apply it. This is where in different scenarios you can toggle on and off the goals and variables, whether they apply or not, because they may not apply in every single scenario. So if they apply in your scenario, make sure you have that box checked. Okay, so now I'm ready to do my GSC. Now, as you can see here, I only have the letter V. I don't see any G's on the workspace. Where are they? Well, if you're doing a group goal like I am right here, then which specific junction should it put the little G on there? We don't know. So that's why you wouldn't necessarily see the G on every single spray nozzle. All right, so I'm going to go ahead and run my model. And that took under 3 seconds to converge. And as you can see from the results, if I go straight to my spray nozzle here, by inspection, you can simply look at these. Excuse me, you can simply look at these and see that the flow rate is above 100 gallons per minute, and the minimum flow rate is right at the ends. And if I go into the goals and variables tabs in the general section, we'll see what pressure we need. So we need a supply pressure of 170 psig in order to achieve our minimum flow rate. So that's what your pump discharge pressure would need to be. So this is a simplified way of being able to model a pump without modeling a pump. I'm just modeling the straight pump discharge pressure itself. And then if I go to my goal seeking control goals, we see here that our goal has been met, but it also tells me exactly which nozzle is hydraulically the most remote, which is J1. That's going to be one of the spray nozzles on one of the ends. And because the piping and the spray nozzles in both sides are exactly symmetrical, then both of these two spray nozzles will basically exactly have the same flow rate there. Now, as I mentioned, that is not always the case. So we wouldn't necessarily just want to say, make this one and this one be my minimums. That's where it's better to use a group goal. So let me pull up an additional example where it's a little bit more complicated to really illustrate where the group goal is highly needed. Okay, so this is a system that is a fire system, which comes as an example right out of the NFPA 15 code. And I'm going to skip right to my GSC scenario here. So when you look at this piping system here itself, which spray nozzle is the most remote? Well, there's no possible way to be able to determine that simply by looking at this system here. It depends on the hydraulics of each individual flow path to every single spray nozzle in the system. So this is a case where you cannot just say, I want the minimum to be based upon this guy right here, because that very well may not be the furthest away. It could be a situation where maybe this spray nozzle is actually the furthest. You have no way of knowing, and this is where it's incredibly useful to allow the goal seeking control module to figure it out for you. Now, in this particular model, that group goal, or that group, is already defined. So if I hit F6 on my keyboard, it brings up the select special window, which can also be accessed from the edit menu right here. So if I go into the select special, I can select things on the workspace based upon different types of criteria. In this case, I'm going to do groups. So in this model, I have two groups. I have an NFPA flow path, and then I have a spray nozzles group. I'm going to select the spray nozzles group and then select the junctions in that group and click OK. So what I already did was I selected these junctions on the workspace. We went in here to groups and then create, and then we created a group for all of those spray nozzles. As we can see, we have a little V defined down here for the supply pressure. So it looks like we've got GSC parameters defined, which we do. So if I go back to the analysis menu and then the goal seeking control manager, I'm using the same type of variable that I did before. I'm changing the supply pressure in order to achieve a minimum flow rate. I'm going to delete that second row because I don't need it here. All right, so the minimum flow rate that I need to be able to achieve through all my spray nozzles is 42 gallons per minute. So this is my group max min goal. Now I want to point out something in this particular scenario. Here I have selected all of the spray nozzles on the workspace because let's assume that this represents a building and the entire building is on fire. Well, if the entire building is on fire, then I want to make sure that each and every single one of these spray nozzles is spraying the minimum required flow rate, which is 42 gallons per minute. Now, that may not always be your scenario. You may not have a scenario where every single spray nozzle is actually turned on. What you might have is a situation where these particular, this floor here is not operating. Maybe you only have a fire going on this level. So what you would do in that particular case is you would select all the pipes and junctions in that flow path. You could turn them off. That way there's no flow in that piping system there. And then when you go to create your group, you would only do your group of spray nozzles in this section right here. So this will actually change the answer. If you were trying to modify the supply pressure in order to figure out which is the hydraulically most remote spray nozzle in this system, it's going to be a different supply pressure, and it could be a very different spray nozzle. And this will be the case depending on any different combination of pipes and junctions that you may have turned on or turned off. So you might consider doing some additional scenarios just to make sure that you know exactly what supply pressure you need based upon different scenarios where different spray nozzles will be on or off in that case. In my scenario, I'm assuming that everything's on fire. So if I go back into my goal seeking control manager for my goals, I have my group goal, which is a group max min, and each spray nozzle needs to be 42 gallons per minute. Again, there's no way to be able to tell which spray nozzle is the most remote. So if I go ahead and run this, it converges very quickly, takes less than 5 seconds. Which spray nozzle is hydraulically the most remote? Well, if I go straight to my GSC goals tab, it's this one right here, J9. J9 has the true minimum flow rate, and if I was to take this one step further, I can generate a NFPA report based upon that spray nozzle. Where is J9? If I do, if I do Control F on my keyboard, I can use the find feature. That's where J9 is right there. Now, if I go back into the output here, I can minimize this panel and I can go to my spray discharge and I'm going to sort the results. So here's my column of flow rates. I'm going to move that over to the left and I'm going to sort these junction results by ascending volumetric flow rate. So here we can see that on the top floor, we have between 42 and 44 gallons per minute. And on the bottom floor, we have 110 to 136. So that would be important to know, is that if you have a system where the entire building is on fire and you have this system alive and this system alive, this system is going to be throwing out a heck of a lot more flow than this system is. So again, that would be something worth knowing about. Maybe you might need a control valve that you put in there to limit the flow perhaps. All right, so if that's a case where using the goal seeking control goals for a group max min is really useful because you can't tell which is hydraulically the most remote. Here's another situation where GSC is incredibly useful, is in this cooling system. So if I open up this cooling system here, it's a very simple system, and I have 3 heat exchangers in parallel. Again, by inspection, if you just look at the system itself, it looks like this would be the hydraulically most remote heat exchanger, which in this example, it actually is. But again, it may not be. You very well could have different hydraulics in these, and maybe this would be hydraulically the most remote. Maybe people went in there and they changed the piping in this flow path, and it's a very small diameter pipe, and it takes out a lot of frictional losses, and they didn't do their job properly. So again, I'm going to use a group goal in this particular example. So here's my scenario, is I'm going to go to the GSC example scenario. In this example, I have one pump that is only operating, and I've got 2 goals and 2 variables. This is where GSC is incredibly useful, is when you have multiple goals and multiple variables in a single system. When you have multiple goals and multiple variables, trying to change things together at the same time is a lot more difficult, especially when you have a complicated system with different flow loops and control features and things like that. So I have a pump with a pump curve, and then I have a pressure reducing valve, which is controlling the pressure downstream to 50 psig. In addition to that, on the optional tab, I actually went in and specified a open percent versus CV table. So if you specify that data, it's really helpful because then you can determine what your actual open percentage is for your control valves. So here's where I've got multiple goals and multiple variables. I'm going to select these 3 heat exchangers, and I'm going to create a group. I'm going to call them heat exchangers. And so now I've already got GSC defined. I'm going to delete everything and start from scratch so you can see what we're dealing with here. Okay, so I have a couple of constraints. I have a constraint where each of my heat exchangers requires a total of 150 gallons per minute. So I need 150 gallons per minute minimum flow through each heat exchanger. The second thing that I need to accomplish is when my control valve here is opening and closing in order to regulate the pressure right here, I need to make sure that my control valve maintains good controllability for its lifetime. So I want to ensure that the open percent for my control valve is at least 30% open. So those are the two goals that I want to achieve in this system. The way that I'm going to accomplish that is by changing the pump speed on the pump with a variable speed drive, and also by changing the control valve set point itself. And yes, you can have a goal and a variable on the same object at the same time. And this will show you how. So I go into my Goal Seeker Control Manager, and I'm going to create a new variable. The first variable is going to be a pump, and I'm simply going to change the pump speed, and it's going to be based upon pump J4. So that's my first variable. Second variable is going to be the control valve itself. So I'm going to change this to control valve. I'm going to change the control valve set point. So those are my two variables. Then my goals, the first goal is going to be my flow rate through the heat exchanger. So I'm going to do a group goal, and it's going to be a group max min, and I want it to be the volumetric flow rate. As you can see, there's tons of different parameters that you can set as your specific goals. So this is going to be 150 gallons per minute for these heat exchangers in that group. Second goal is going to be a point goal, and it's going to be the control valve. So my control valve open percentage needs to be at least 30% open, and then it's going to be based upon J8. So now I have two goals and two variables in the system that will change together as the model runs. Fathom does this really well. This is where you really want to use the GSC modules when you have multiple goals and multiple variables in the system. And even for a simple system, it can take a very long time to solve if you're trying to do it manually by hand, and this will just let GSC do it for you. Once in a great while, depending on your system, it may take a while to solve for GSC, much longer than a regular Fathom run. That's okay. That's because not only is Fathom doing potentially tens of thousands of iterations on pressure and flow, it's also tweaking your variables hundreds of times in order to help you meet the goals that you have in your system. And if you're trying to do it by hand, you can run into situations where you've got complicated system interactions and maybe there's no potential solution. So that could be an answer, is it might tell you that there is no possible way for your goals to be able to be achieved. Well, that means something has to change. Either maybe the model is not modeling things properly, maybe the design is not good, or maybe your flow measurements are off. Those would all be things to look at. So here, if I go to my GSC variables, I can see what my resulting pump speed and control valve set point would need to be. So my pump speed needs to drop down to 93% speed, and I need a control valve set point of right at around 45 PSIG. So those are my GSC variables. That's my answers that I was looking for. Next is if I go to the GSC goals, I can see that I specified a minimum of 150 gallons per minute, and I achieved a minimum of 150 gallons per minute. And again, it tells me which junction was the most remote. So that's good. And then I can also see that my control valve open percentage is right at 30%. So those results I'm very happy with, and this was able to do it very quickly, much faster than I can do it by hand. So this is an example of doing multiple goals and multiple variables at the same time. Two more examples that I want to demonstrate here. One is another multi-variable, multi-goal example. And if I go to our tips and tricks page, one of our outstanding applications engineers, Scott Lang, wrote this excellent blog article. It's called Reaching Equilibrium, System Energy Balance in AFT Fathom and AFT Arrow. This example is not necessary, or this tips and tips, sorry about that, everyone. This tips and tricks article is not really intended to discuss the goal seeking control module. It uses it. What it's really trying to do is show a closed system and how AFT Fathom handles closed systems thermally. So this is a really interesting example, and I asked Scott to send me the example, and he did, because there are multiple goals and multiple variables in there. So let me go ahead and open that model up for you. Now, just one thing I want to know is that the model looks prettier in the blog article itself. I would need to clean this up a little bit. So here's what we have going on is we've got a couple of three-way valves. This is the three-way valve junction. The three-way valve allows you to specify a combined flow pipe and two split flow pipes, and you can change the open percentage. And this is how you can change the amount of flow through one path or another by using the three-way valve. That is this junction right here. So that's a really useful junction that you might use for doing recirculation lines or bypass lines, or trying to get more sophisticated temperature or flow control. So here we have 4 goals and 4 variables. And this is a pretty complex system. It's doing heat transfer, a lot of calculations. These 2 heat exchanger junctions represent the same physical heat exchanger. So one of them would be a shell side, the other would be a tube side. And if I open up my goal seeking control manager, we can see what variables and what goals we have specified here. So for the variables, we're changing 4 things. We're changing the open percent in the three-way valves, and we're changing the loss value for these 2 valves before the flow comes back into the hot and cool fluid pools that the piping is in. So those are our 4 variables, and then we have 4 goals as well. And we have 2 different types of goals. We've got temperature goals, so we want to make sure that the temperature at the outlet of each of these pipes, which happens to be different, 100 and then 75, we want to get those temperatures at the outlet of each of those pipes. And then we have a flow requirement of 50 gallons per minute through each of those pipes as well. All right, so if I go ahead and run this model takes about 45 seconds or so to be able to run and get to a point of convergence. So while that's going on, I want to open up our examples help file really quick, because if you, even if you do not have access to the goal seeking control module, you can still read through our tutorials to learn how to use those capabilities. So if you browse to where the software is installed on your computer, there's this examples folder, or let's say that somebody else is using the license. If somebody else is using the license, you wouldn't necessarily be able to open Fathom, but you could still browse to this location, and this is where you can find the examples help file. This is our help file, which contains all of our walkthrough tutorial as examples. So if I open this up here, this is our examples help file for Fathom, and these are all the base non-module examples right in here. But if I go down and I expand the section for Fathom module examples, here's all the different examples that talk about the goal seeking control module. Then we also have extended time simulation module, settling slurry, etc. And so if you go to those different tutorials, this will walk you through the process of how to build these different types of systems and do these different types of analyses. All right, let's take a look and see if Fathom is done yet. I guess it's taking a little bit more than 45 seconds. Again, it's okay, because sometimes you've got a really complicated system. Here, we only have 45 pipes and junctions in our system. It's not a very big network. However, there's a lot of complication going on. We're doing heat transfer all throughout the system. We've got a couple of pumps. The pumps introduce significant amounts of nonlinearities. We've got a control valve. We've got three-way valves. We've got the goal-seeking control module being used. So do not be surprised if it may take a few minutes for your model to run when you're doing something like this with the GSC module. Again, this is doing it way faster. You can come up with those results doing it by hand. So if I click on the output to look at the results, it just took 2 minutes in this case. And as we can see here, we know what the open percentage is for each of those three-way valves. We were able to go in and size the two regular valves. So the valves need to be slightly different. That's what you can determine with the different CV values there. And then finally, we've got our temperature and flow rate goals. So as you can see, we were able to achieve the temperatures that we needed as well as the flow rates that we needed. So just another example of multiple goals and multiple variables in a single system. All right, last example that I want to show you today. It's pipe variables. So this is where I talked about how you would do model calibration typically, where you would change the pipe variables themselves in order to get the flows and pressures that you might want. So again, if you go into AFT Fathom and you click on the example model calibration with pipe variables, this example will walk you through exactly the process that I'm demonstrating here. So I have a very simple system, and in the initial system, I've got steel pipe, and the steel pipe is clean. It's brand new, so this is the absolute roughness in each of the pipes right here. So based upon this particular system here, we're going to get a flow rate based upon the elevation differences. So here, the flow rates in my system are going to be, it's going to be 2,000 gallons per minute. So that's our brand new system, 2,000 GPM. Well, 10 or 15 years later, we take a new flow measurement and we're only getting 1,600 gallons per minute. Well, why is it only getting 1,600 gallons per minute? There's no control valves in here. Well, that's this scenario. So in this particular scenario, in order to match the results, I'm going to change the amount of friction inside the pipes in order to meet the flow rate that has been measured in the field. So if I open up one of these pipes here, what I'm actually going to be changing is the absolute roughness value itself. So again, this is only a starting point. There are different ways that you can skin the cat on this. You can also change the inner diameter reduction due to scaling, or you can do something a little bit more simplified on the optional tab. You can change the design factors themselves in order to get the flow rates that you want. If you were to go to our website, AFT.com, we have several case studies that demonstrate model calibration. And now one of the ones was the system for the Duke McGuire nuclear plant. And so that's an example where we used pipe variables by changing the roughness inside the pipes to get the flow rates and pressures that they were measuring in the field. Okay, now this particular system here, I have several different variables. I've got 6 variables here. As you can see, there's a variable for changing the friction on every single pipe. So I have a V on every single pipe. Now the thing is, I don't want each of those individual pipes to end up having different roughness values, because that's typically not going to be the case. So what you would do here, in order to keep from over specifying your system with having way more variables than goals, my only goal is that the flow rate is now 1,600 gallons per minute. And I'm referencing it to the last pipe, but any of those pipes would work. So I only have one goal. Well, in order to break this down from 6 variables down to 1, is what you would do is for each of these additional variables here is in the link to column, you would link them back to the first one. So what that would do is it would change the variables for each of those pipes together. That way, each of the pipes will end up having the same roughness value at the end of your iteration process. So that's how we still have a unique 1-to-1 ratio where we effectively have one variable per goal. So if I go ahead and run this example, it goes pretty quick, less than a second. If we take a look at the GSC variables, this is the new roughness that was calculated inside the pipe, 0.016 inches, which does not seem to be very much. But if you compare this with the clean pipe absolute roughness, which is 0.0018 inches, then this is actually about 7 times more frictional buildup inside the piping. And we can also see that the GSC goals have been met. So if you've got significant buildup where it's 7 times more friction inside your pipe, it might be time to go ahead and replace the piping in that system, especially if you're not getting the flow rates that you actually need. All right, so that is the goal seeking control module and the examples I want to demonstrate and how you would be able to use it. Again, it will make your iteration process much, much faster. It's a major time saver, so very much worth investigating. If you want to try out the goal seeking control module, please feel free to contact me. If you're within the United States, sales@aft.com. We'll be happy to get you an evaluation. If you are outside the United States or if you work with a channel partner, contact our excellent channel partners and they'll be able to help you out with an evaluation as well. Thank you all very much for your time today and for listening in, and we will look forward to seeing you in the next webinar. Take care, everybody, and have a wonderful rest of your week.